Hello to everybody. So this is going to be the first part of this course on geometry and arithmetic of curves over finite fields. So as I explained in the guiding lesson, I'm not going to repeat the notes. So you really should navigate between what I'm going to tell you now and the notes. And so in this course, what we are going to study is the chapter 2. Chapter 1 is just the introduction in the notes, so this is really about chapter 2. But again, I'm not going to repeat what is written. So what I'm going to do is I'm going to do a kind of long companion example. And by this companion's example, I'm going to restrict not to study all kind of curves, but I'm going to study in this precise example that should serve as motivation for all my course, plane curves. So let's do this. We are going to study plane curves over a field K. And I'm going to assume that K is perfect. So a perfect field, you can of course think about K of characteristic 0. K algebraically closed. Okay, what is going to be of main interest for us is a finite field FQ. Okay. All right. So the definition I'm going to use. So this is definition 2.1.2 in the notes. So I'm going to define, given f a polynomial in two variables over k, I'm going to define C of f as the set of A and B and k bar square, such that f of A and B equals 0. So, well, you have of course, example in mind. If you take f x squared plus y squared minus 1, then, and if you take k equal r, then you are going to look at all the complex points of the circle. So CF is going to be all complex points on the circle, the unit circle. Of course, I can't draw it because, well, I can't draw in C times C. So, I'm a bit restricted here. But we will see, how it means then to restrict to the points over K. One important thing behind this, behind all, let's say, the philosophy of algebraic geometry, because, we are going to consider algebraic element and the geometry of it, is that there is a kind of duality correspondent between the algebra on one side, which is the curve f, and the geometry on the other side, which is C of f. And of course, it's not perfect. F determines a C of f by definition, but maybe C of f doesn't determine completely f. But it is not difficult to see how it fits together. And how it fits together is this famous null Stellensatz, which is exactly the result theorem 2.1.1 in the note. All right? And it tells you that more or less, let's say roughly, the curve is going to determine as well the polynomial f. And this is really important because most of the time you're going to see that I'm going to express myself in one of the world or in the other world. And this goes quite far away because, for instance, speaking about how f factors as a product inside k bar of xy, for instance, is going to tell you how the curve CF decompose into components. So sometimes I'm going to say, let's study the components of the curve CF, and sometimes I can say, let's study factors of the polynomial f. And I'm really going to use it freely, so if you're not comfortable with that, that's the point also where maybe you should stop a bit and look precisely at this Null-Stellensatz theorem and also at some of the consequences that are explained in the exercise in this part. But really for me, I mean, this is really to be a base ground. So once we have this, then I mean, we are also interested not only in the geometry, and by geometry I mean considering the object only over k bar, but also over k. And so we are going to look at rational points. So what I'm going to denote, so let's say we have k, and I can take any k prime, any field between k and the algebraic closure. Then I can speak about k prime rational points on CF. So as you can guess, they are just going to be the set of points AB, where now I restrict to k prime, which are going to be on the curve. So this is going to be called the set of k prime rational points. And so, for instance, now I can draw it. If I take my example with f x squared plus y squared minus 1, then what is CF over R? Well, it's exactly the unit circle. Okay? Very good. I mean, one exercise that we can maybe try right now. So that's the point where I'm going to state an exercise, and you should try to stop and try to see if you can solve it. It could be nice to look at this set of rational points in another way. So I'm going to say that P, a point on k bar, so any point on CF. So I mean, this is exactly also CF with my notation. Then P is a k rational point if and only if for all elements inside the Galois group k bar over k. So this P, I'm going to denote it with coordinate A and B. I want P sigma, which is by definition the action of sigma on the coordinate, to be equal to P. All right? So you can think about this. One maybe piece of advice is that you might not be very familiar with gal of extensions which are not finite. But this is really not a problem, because a point which is in CF of k bar, it has to be inside some finite extension of k. So you can really think that everything is finite and you're going to consider only finite Galois group here. All right? I mean, this is just a convenient way to store all the extensions together. And so why do I state this exercise here? Because I think it shows you that somehow studying rational points on a curve is doing geometry. Okay? You take all the points and then you apply some Galois action. Okay? And in that sense, it tells us also why it is maybe easier, and it is easier in practice, to study rational points over finite fields than over number fields, because over number field, this Galois group is already awful. When you are over finite fields, we know that, this Galois group is generated only by one element, which makes life easier for everybody. Okay. So now we have curves, plain curves only, but curves. We have finite fields. We have rational points, and we would like to say, okay, genus, but we don't know what a genus is. So I'm going to replace it by something. As I said, this is like a guiding companion example. So here, what is going to be the replacement for the degree? What is the complexity that you want to use? I think it's quite clear. So we are going to replace genus of a curve. We are going to replace it by the degree of f. So the degree of polynomials is the maximal degree of all the monomials that appear. Okay, so, and I'm going to call then, if I take f, so if I fix now the finite field fq, I can look at what I'm going to call nqd, which is the maximal number of points of, so the maximal of the cardinality of CF FQ when F is inside FQ XY of degree D. Okay? So this is going to be the cardinality of this set when I run f over all polynomials of degree D. Okay, so first, I think it's a good analog. For people who know a bit more, because now if I restrict to degree D over FQ, the set of possibility for f is finite. And maybe this is going to be a good quiz test. So what is the cardinality of the set of polynomial in two variable over FQ of degree D? Okay? You can also try to solve this. So as you see, it is going to be a quite big number. It's going to be big when Q is big and the degree is big. It's going to expand very quickly. So it's hopeless at some point to try to solve this problem by just enumerating all f and looking at and computing this number of points. At some point, this is going to stop. There is a finite power of computation right now. Even if you use all the powers which is available on Earth, you're not going to solve it as soon as, let's say, D is, let's say, 10 and Q is 100. Okay? So we have to try to solve this problem in another way. And maybe, the best way to start is to solve it for small value of D. Let's try to have some intuitions of what is going on for small values of D. Okay, so new quiz. I give you to do the case D equal 1. All right? So now that you have done it, I mean, you see that in that case the situation is quite easy, and that the numbers that you find is that nq of 1 is q. All right, let's move to d equals 2. D equals 2, we are going to do it together. It's now that I'm starting to speak either geometrically or algebraically. So I'm going to start, speaking geometrically. So the situation with the degree 2 polynomial is that the curve of degree 2 could be, for instance, 2 lines. So you could have CF can be, first case, 2 parallel lines. Okay? So, well, if you have 2 parallel lines, you are in the case of degree 1 twice. And as the lines are parallel, they don't have any common points. So how many points do you have in total? You have the number of points on one line, which is q, twice. So here you would have 2q rational points. Okay, another possibility is that your polynomial f is the square of a degree 1 polynomial. In that case, what you have is one unique line. Well, if you have one unique line, you have q rational points. This case is going to be less interesting. Is there another case where your polynomial f is not irreducible? Here we have done all cases where the polynomial f is going to decompose over fq. But maybe it is irreducible over fq, but not irreducible over fq bar. So these are two notions that we call irreducibility or absolutely irreducibility. So let's take now the case where CF is not absolutely irreducible. So this is the case where f is going to be the product of two lines which are conjugated. So L and L sigma 0, where sigma 0 is a generator. Well, and so that you know, of course, the generator of the Galois group, it's quite easy. As I said, it's simply that x is mapped on x to the q. Okay? All right. So you have like two lines like this which are conjugated. So let's try to analyze how many points this can have. So this is an exercise, that you can try to do. Prove that the number of points, of rational points on such a curve, well, this is not going to reach any record because it is 1. So let's try to understand this. So you have two conjugated lines. So let's say 1 and 2. So these lines L sigma 0. First, I say that there is one particular point, which is the intersection point. So let's call it P0. And I say that P0 is indeed rational. Why? Well, P0 is the intersection point. Let's look at its Galois conjugated sigma 0. Okay? So P0 sigma 0 must also be on the line. So it is on the line L, so it has to be on the line L sigma 0. But it is also on the line L sigma 0. And of course, as these two are conjugated over quadratic extension, you have that L sigma 0, this is L. So P0 is also on L. So it is on the intersection of these two lines. But there is only one point on the intersection of these two lines, which is P0. So what you have proved is that P0 sigma 0 is P0. And as sigma 0 square is the identity in that case, you have proved that P0 is inside CF of FQ. But now I say that this is the only point. Why? Take any other point which is not the intersection point. Well, let's take it here. So what is going to happen to this point? It belongs to L. So its image by sigma 0 must belong to L sigma 0. But as it is not the intersection point, it can't be the same point. And so it is not stable by the Galois action, and we have seen that what is important is that it is stable by the Galois action. Yeah, you're done. There is only one point. Okay. So now we have done all cases which can decompose either over K or over K bar as the product of two linear factors. So we are done with this, and we can consider now F, let F donc of degree 2 absolutely irreducible. So we are playing with degree 2 polynomials in two variables, and this is part of the classical topic of trying to classify conics. So if the characteristic of FQ is different from 2, then you know that F, after a change of variable, can be written ax squared plus by squared plus c with abc all non-zero. Okay? Very nice. But first, we might wonder, can I really do a change of variable? Is that legal? Am I really considering the same problem when I say that I'm going to consider it on F or on F which has this form? Yes, because if you do a change of variable, you have like linear polynomials in x and y, or affine polynomials in x and y, which transform your f on this new f. And this is going, of course, to send a rational point on a rational point. So a change of variable which is defined over the field, this is the case. Here, it's a classification over FQ and not over FQ bar. The classification over FQ gives you a change of variable defined over FQ. And so it gives bijection between the points, the rational points on the first curve and on the second one. To study the number is going to be the same. And it is a change of variable which is legal in the algebraic sense. Okay? You have really defined an isomorphism in the sense of algebraic geometry. And if you want to do more, because this is somehow a baby case, this is section 2.3. So study more generally maps in algebraic geometry. If you want to know more about what are the maps which are legal, maybe they are not only affine ones, this is section 2.3 of the notes. But be careful, here, it's done only in the projective case. But anyway, I think you can manage. Okay, so we can start, with characteristic of FQ different from 2 with this, and if characteristic of FQ equal to, meaning that FQ is just F2 to the n, then, there is a result which is maybe less known, is that you can always have f of the form. So let me see, it's x squared plus y, yes. Okay, so let's just finish with this case because it's easy. So what is going to be the number of points in that case? You see that you can take any value of x inside FQ, and each time it's going to give you exactly one value of y. So how many values do you have in total? You have q values. So this one is not to be a record. Let's remember that so far our best value is this 2q here. So this doesn't beat it. Okay, but maybe the first one. So characteristic of fq different from 2. The first thing to look at is to prove that there is one rational point on CF. How do we do this? I mean, this is a quite nice trick. You start by looking at the map. X maps to ax squared plus c. And you're going to look at the map y maps to minus b y squared. Okay? So let's call this one phi and this one psi. What is the cardinality of the image of phi? Well, you know, if you look just at the x squared, it means that you're looking at all the numbers which are squares. How many squares are they? I mean, they are exactly q plus 1 over 2. Now, a is not 0, so you're just doing a bijection, and you're translating. This is another bijection, so what you have is exactly the number of squares, which is q plus 1 over 2. And same for the cardinality of phi, it's going to be q plus 1 over 2. But now the sum of these two numbers, this is q plus 1, which is greater than q. What does it mean? It means that necessarily these two functions must reach at some point the same value. But if they reach the same value, it means that ax squared plus c equal minus by squared, in another sense that there is a point on CF of fq. So this proves that the cardinality of CF over fq is greater than 0. Okay. And now what? Now, well, I'm going to draw a kind of conic. Okay, the circle is a degree 2 curve, irreducible. Now I have my point here. I mean, this P0 that I could prove that is a rational point. And what I'm going to do, I'm going to draw all the lines through this point. And I'm going to invoke another theorem in a trivial way here. I mean, you could do it much easily in another way, but Bezos Theorem, which is in section section 2.4. Well, in that case, you know that there is at most another intersection point, because this is a line, so it's degree 1, this is of degree 2, so there is at most one point. And as this one is rational, this one is going to be rational as well. You could prove that, for instance, with the Galois action as we did it before. So for each line, I'm going to have at most one other point. And how many lines do you have? Well, I mean, a line is given by a slope, and you have q possible slopes. So it means that what you have proved here is that nq in that case, what you have proved is that the cardinality of the number of rational points must be smaller or equal to q. Okay. And as we know that before we had 2q, this is not going to be so helpful neither. So in total, I think that now we have solved all our cases. And what was the conclusion? nq2 is 2q. Well, we have done degree 1, degree 2. What about degree 3? I mean, already in degree 3, the situation starts or seems to be more complicated. Because what? If we start the same analysis, we have already seen degree 3. Remember, we had this x squared plus y squared equal z cubed. X cubed plus y cubed equals z cubed. No, plus z cubed equals 0. Or congruent to 0 modulo p. From Gauss. Gauss looked at this. I mean, if Gauss looked at it, it must not be so trivial. And why is it the same a bit? Because as I said, I mean, if you divide by y, you can look at x over y plus x over z plus y over z cubed plus 1. And this is 0 in Fp. Okay? So when you exclude the point where z could be 0, you're looking at an equation of a curve. Big x cubed plus capital y cubed plus 1 equal as 0 inside Fq. And you're trying to look at the number of solutions. So yeah, this must be already non-trivial. So maybe we need other ideas if you want to go up. The thing is that, well, you can, we can actually give really what the result is going to be. It's not that complicated. Why? Because first, what you do in all these cases of trying to study rational points is that you start by giving an upper bound. And in that case, this upper bound has been proved by Segre. And Segre proved that NQ of D is smaller than D times Q. Okay? So let's see how you prove it. So to prove this, you introduce a new curve. A curve that I'm going to call D, and it looks like a stupid curve because it doesn't depend on y, but I mean this is legal, and it's just going to be the curve defined by the equation x to the q minus x equals 0. Now, what I can do is I can look at the cardinality of the intersection of a curve CF of degree D with the curve D. All right? So if the curve CF has no component in common with the curve D, I mean, what Bezos Theorem tells you is that this number needs to be smaller than the degree of D times the degree of CF. So it has to be smaller than D times Q. Okay. Then what? Then let's consider a point AB that would be a rational point on F, on CF. What I see is that A has to be inside FQ. And this means that we have also A to the Q minus A, which is 0. So what I have just showed you is that the point AB must also be inside D of FQ. So a point on CF is rational if it also belongs to D. So it has to belong to the intersection of these two curves, and we know that the number of points is smaller than D times Q. Now, I mean, there is only one assumption that I have made at the beginning, is that CF and D don't share any component. But now, D, I mean, is going to be, I mean, you can factor it as a product of all vertical lines, I think. So what you're saying is that you're asking F maybe to have a linear factor. But if it has a linear factor, then we have already treated this case before, and we could remove it until there is no factor, and you can prove the same kind of bound. Okay, but this gives us an upper bound. Can we do a bit better? And can we really say what is the number of points? So, I mean, there are two cases. I mean, you can first suppose that Q is bigger than D. All right? So if Q is bigger than D, it means that you have plenty of space inside your finite field FQ. And we have already now an intuition of what could be the best case because we have studied the case of degree 2. And for this, we could take now D lines. Take D parallel lines. I mean, there is place for this because Q is bigger, okay? You take a line x equals 0, x equals 1, and so on until D. So you take D parallel lines. Well, if you do this for the curve, I mean, this is going to be your curve CF. And it means that the number of points on CF is D times the number of points on the line, which is Q. And you get Q times D, which is the maximal you could hope for, so you're fine. Now if Q is smaller than D, then what can you do? Well, then you still take Q lines and complete with whatever you want. With an arbitrary curve of degree D minus Q. Well, how many points do you have? Already with these Q lines, you have Q times Q, so you have Q squared. So the number of points has to be bigger than Q squared. But this is a curve which is inside the affine plane. It is inside A2. So the number of points has to be smaller than the number of points on the affine space, which is Q squared. So you're done. I mean, you have two inequalities, and so here you get that the number of points is Q squared. All right, so in both cases, you have solved the problem. So it was not such a hard problem at the end, right? Well, what do we do when we have solved a problem in math? Then, I mean, we try to find a new problem. I mean, we never stop somehow. That's the idea, right? And how to find a new problem? I mean, how to find a new problem is to say, okay, maybe my problem was easy because I let something happen. And here, what was the thing that happened that really helped us? Is that each time we were taking lines. So a nice way to get a problem that won't be maybe that trivial is to remove this hypothesis, okay? This facility. We are going to say that now we are going to consider the same problem, but where we are going to take curves with no linear component. So let me see, that's page 4. Okay, so constraint impose no linear component. And then indeed the situation becomes more difficult because it was until 2010 a conjecture. So a conjecture that was called slick lie. I'm not sure I pronounce it correctly. Conjecture. And it was solved in 2010 in a paper from Omar and Kim. And I'm going to state this conjecture, and so which is not a conjecture anymore. So if you take C, a plane curve of degree greater or equal to 2 over FQ without FQ linear component. All right? This is now our assumption. Then the number of points of C over FQ is smaller or equal to D minus 1 times Q plus 1, unless one example of degree 4 over F4. Okay. And now I just noticed that I forgot something. Okay, because this conjecture is indeed for plane curve, but is not for plane affine curves as we have studied them until now. So this is a plane projective curve. So before imposing this, this constraint, I should have said something here that. So the first thing we are going to do is to move projectively. So pass from affine curves to projective curves. Why do we want to do this? I mean, it's not because it's going to make the problem much more complicated if we didn't impose the linear component. It's because actually it makes things easier. I mean, we have seen several times that it was a bit annoying not to work projectively. I mean, what do you gain when you work projectively? For instance, Bezos Theorem is much better. Okay, Bezos Theorem, you can really state it as something which is going to always give you that the number of points in the intersection is going to be the product of the degree if you count them in a right way. So Bezos is better. What is better also? I mean, first, when we studied the case of degree 2, remember, we had like this case where we had like crossing line, parallel lines. The thing is that projective geometry, it helps you to unify all these. Two lines always intersect. So somehow, it decreases the number of cases to consider. It's a more unified situation. Other nice thing is that we can have different conics over affine. You know the classification of conics. Over the projective, they are all the same. All conics are the same, for instance. Up to change of variable. So all irreducible conics are the same. Well, maybe we are looking for reasons which would be a bit more profound. One of them is that you will see later that there is a nice dictionary between curves and function fields. And when you look at it like this, function fields, they have not points, they have something which are called places. And if you really want to have a complete dictionary, it's better to study projective curves. Then you have a complex dictionary. So link with function field. And I think I have one more reason to give to you. We will see in the next chapters, and when we are going to consider functions on curves, and also morphisms between curves, that all these, they behave much nicer. You have unified theorems that tells you that something is always equal to a degree or something like that. And this works only when you work projectively. So all functions, morphisms behave nicer. Okay. So that's plenty of reason to move projectively, and that's why also this conjecture and all the work that is done on curve is mostly done, I don't say 100%, but almost everything that I have seen is for projective curves. So yeah, you have this conjecture. Of course, if it has been solved only in 2010, I'm not going to prove it here. That's not the point. But I just wanted to give you a small overview of how far you can go in this direction. And the nice thing is that, so this gives you an upper bound, and of course we have the problem. I mean, can this upper bound be reached or not? And the first result is that if, again, the degree is big, so it's bigger than q plus 2, then the bound is sharp. And even you can find, so it means that you can find a curve over fq which reach q squared plus q plus 1. And so what is this q squared plus q plus 1? It is, it is the number of points of P2 over Fq. So it is the number of points of the projective space, and so obviously you can't go much further. All right. Well, actually, the bond is not sharp. Because, I mean, this number is going to be smaller than this when d is going to be big. So what I mean is that if d is greater or equal to q plus 2, a sharp bound is known, more or less. Or let's say the exact value is known. And if I state it like this is not going to be fine. I should have introduced something for the maximal number. So is known, meaning that, well, I should have introduced something more, I think. Let me phrase it like this then. So the exact value is known, but the exact value of what? So let's call it mqd, which is the maximal of the number of points, of rational points, when f has no linear component of degree d. And so what I mean is that in that case, mqd is equal to this value, and this is exactly the number of points on P2 of Fq. Sorry for that. Okay. So, I mean, when d is big, one has a solution. And what for other things? I mean, in general, the situation is not solved. I mean, you have like known result. Well, of course, when d is small, I think up to maybe d equals 4, I mean, things are known. And then you have some sporadic value, q plus 1, q minus 1, square root of q minus 1 when q is a square. I mean, these are more or less where people know the values of it. So do we know much more? Actually, I mean, there are like a bunch of results in this area where people have studied like medium value of d in comparison to q and so on and so on. But I don't want to enter much more in this area because, I mean, the topic of number of points of plane curves is not really the one we want to focus on later. But then, I mean, why? Because in the conditions that I'm going to impose to my curves, is I'm going to impose them to be non-singular. So I'm going to concentrate on non-singular curves. And non-singularity, I mean, this is a condition that you may have known in other contexts of, like, for instance, analytic geometry. And you can see the definition of what is going to be non-singular just given by the Jacobian criteria, or like also the Zariski characterization, at definition 2.1.7 inside the notes. And can I always impose non-singularity in this work of plane curves and reach the upper bounds? One very nice result is that, yes, I mean, at least you can prove that, for instance, that when D is Q plus 2, you can find there is a smooth means non-singular, it's the same, plane curve, plane projective curve of degree D over FQ with the maximal number of points we had before, Q squared plus Q plus 1 rational points. So, I mean, this is really a strange object if you think about it. It is a plane curve which is not going to have any singularities and which is going to fill all the rational points in the projective space. I mean, it's a nice example, and I mean, this has been obtained, for instance, also in an article of Homa that we might study a bit in exercise later, which is called non-singular plane filling curves. Okay, so the thing is that we want to deal with all non-singular curves. And the question right now is that could we hope that all of them could be represented by a plane model? And unfortunately, the answer is no. I mean, we will have to deal with other models which are not plane. And in order to show that to you, I'm going to give you an example. So I'm saying that there exists a genus 4 curve, smooth, projective, and actually absolutely irreducible. So it's going to be a nice curve for us, absolutely irreducible here. I'm telling it, but it doesn't play a role. With 8 rational points over F2. And why is that a contradiction first? Well, because 8, this is bigger than the number of points you have, the number of rational points you have in the plane. So in the projective plane, you have 4 plus 2 plus 1. This is 7. So, I mean, you can't get a plane smooth model of your genus 4 curve inside P2. All right, so what is this curve? I mean, so I suggest that you try to do this as an exercise. So the curve is going to be given by these two equations. So first, a cubic equation. And a quadratic equation. We'll see in the third lecture that this is indeed the canonical form of a genus 4 curve. So xt plus yt plus zt plus t squared equals 0. So this is a model inside P3. And so first, using really the definition, the Jacobian criteria that is stated in the course for affine curve, but here you have a projective curve, so you will have to cut affine charts. But once you do that, I mean, then it's just to apply the definition, and then you prove that C is indeed smooth. The question B is to prove that it has 8 points over F2. So in order to do that, you have two solutions. Either you do it by hand, you replace all the possibility of x, y, z, and t by 0 or 1, and you see when a point satisfies these equations. Or you can try to program it, if you know how to do it, with a software. I mean, and this is, of course, going to be much faster if you know how to do that. And the last thing, I mean, I stated it here, so you can try to prove it too, that C is absolutely irreducible. And this is a bit more the tricky part. Because what you have to prove is that you have to prove that the ideal generated by these two equations is a prime ideal inside F2 of x, y, z, and t. And in order to do this, what you're going to use is the fact that this ring is, it has the property that it is a unique factorization domain. So, meaning that your ideal is going to be prime means that you can't factor it as a product of two ideals. And the first thing that you will do is try to play with the degree 2 equations here that you can see in this ideal is going to be unique equation or generator of degree 2. And see that what it would mean that this is going to factor or not. So this is what I can say. So yeah, first thing we have to notice is that we can't restrict to plane curves only if you want to consider all smooth curves. One last thing is that you might know, from all the courses that you had about curves, that geometrically at least, any curve, any smooth curve, has a model, so a smooth model, I should maybe, in P3, when you consider this problem geometrically. So this is really nice. Somehow, you could represent them, all of them, inside P3. But again, this is only true if you think geometrically. And in order to find a counterexample to show that you can't maybe put all smooth curves inside P3 over a finite field, you would have to go a bit higher. But looking at manypoints.org, you find an example. So there exists a Genus 14 curve, so this is quite high, over F2 with 16 rational points. And again, why is that a contradiction? Because 16, this is bigger than the cardinality of P3 over F2, which is 8 plus 4 plus 2 plus 1, so 12, 14, 15. Okay? All right, so that's the end for today.